Right. Good morning, everyone. So we are recording now, and let's just see what we did yesterday. So we started with an arbitrary linear program, which had all sorts of strange things going on, right? All sorts of inequalities were there, and we transformed this into a linear program in standard equality form, right? We followed a bunch of steps, and using these steps, you can convert any arbitrary linear program to a standard equality form linear program, which will be equivalent to the original linear program, right? So in other words, if you solve the standard equality form linear program, you also solve the original linear program. You can also get an optimal solution to the original if there is an optimal solution. So from now on, we are going to focus on linear program written in the standard equality form. Okay? And I have just rewritten this linear program here at the end. Okay, so this is exactly the same linear program that we got yesterday. The variables have been renamed from x to x1 to x6. Why not? And let's say we want to solve this linear program. So what do we mean by solving a linear program? Remember the fundamental theorem of linear programming? We know that for any linear program, either it is infeasible, or it is unbounded, or it has an optimal solution. One of these three possibilities holds. Exactly one of these, right? So when we say solving a linear program, what we mean is either we find an optimal solution if one exists, right? Otherwise, we conclude that the linear program is either infeasible or unbounded, whatever the case may be. Right? So this is what we want to do next. We want to solve linear programs. Okay. So let's look at this one here. If you look at this linear program, supposing I ask you, can you find a feasible solution? Right? It's not even clear how you would find one. Like optimal is an even more difficult question, but even it's not clear how you would find a feasible solution by just looking at this linear program. Right? So let's do something easier today. Let's look at a special type of linear program, and we will see later how to get to that special kind of linear program later. Okay, but I just want to start with an easier linear program today and go through the simplex method, how it finds an optimal solution. Okay, so I'm going to change the page and write a new linear program, which is going to be different from this one, and it's going to be easier to find a feasible solution. And from there, we will go to an optimal solution. Because the linear program I've chosen has an optimal solution. So later we will look at the other possibilities. Okay. So we will consider a linear program that is clearly feasible. Okay, and what I mean by this will become clear shortly. Okay, so here is the linear program I want to consider for today's lecture. So it has 7 variables and 3 constraints apart from the non-negativity constraints, and I'm writing down everything in a matrix vector format.
Sir, I had one question here.
Yeah, go ahead. Go ahead.
Sir, here these zeros at the end, they are the slack variables, right? So the zeros are for the slack variables.
It's not clear.
It's not
we
clear.
didn't go through the transformation.
Okay, so then what are those for?
Well, I'm just. I think there is some echo at your end.
Okay, sir. I'll just.
So when I speak, I hear my voice back.
Okay, now it is better.
Now I don't hear myself. Yes. Okay. Good.
Okay.
Yeah. So, I mean, let's not worry about how the transformation happened, right? So we have some linear program that is already in standard equality form. Right? So I don't want to mention what is a slack variable or not. This is just the linear program we have.
Okay.
We are not going through the whole transformation. So I don't want to assign any variables as slack variables, right? The important point is that any linear program can be converted into standard equality form. And now we are just going to focus on the standard equality form linear programs.
Okay.
Yeah.
So, and one more thing that I wanted to ask was, if we add the slack variable, we just say some epsilon or some xn or something that we were adding. But that value can have any coefficient, right? I can have 2 times x6 or something, and then x6 will automatically adjust to whatever it should. So if it should have been 6, it will become 3.
Yes. So long as you are keeping the sign correct, the coefficient doesn't really matter. It is standard to keep the coefficient 1, but you could actually choose whatever coefficient. But then you have to, in the transformation, I guess you just ignore the slack variable, so it doesn't matter. Yeah, that's right.
Okay. Yeah.
But the standard practice is to choose 1 as the coefficient.
Yes, it makes life simpler.
Right. Okay. So this is our linear program that we are going to consider for today's lecture. Okay. And if you look at this linear program, can anybody find a feasible solution? I want you to observe this linear program and find a feasible solution that is easy to find. Observe the matrix and see if you can use the matrix A to easily spot a feasible solution.
Sir, what we could do is we could make everything 1 except for x5 and x5 and x7, sir.
Okay. Everything would be, yeah, go ahead.
So like it was, all the sums were pretty close to the values in B. So I thought you could make x7 2 and let's see this x5 equal to 6.
I want you to do something even easier. I want you to observe the,
like we have a 1 1 1, right? So you just take x5 to be 17 x6.
Yeah, that's the easiest way to go about it. So I want to do that. I want to look at this here, and this is an identity matrix. It is not a coincidence. It was deliberately chosen to be 1. And now you can clearly read off a feasible solution. Set all the variables to 0 except for the last 3, x5, x6, x7. Set them to the right hand side, 17, 4, and 10. And that is a feasible solution, right? Okay. So, yes, there is an easy feasible solution, and that is just 0, 0, 0, 0, 17, 4, 10 transpose. Okay. Sometimes I may put commas, sometimes I may not. Don't worry about it. Okay. So this is easy to spot because the matrix has some special form, right? And this is a feasible solution. So we are going to start with this linear program. Notice that it's a feasible solution, but we don't know whether it is optimal. Okay. We want to get from here to an optimal solution using the simplex method. So what we are going to do is we are going to rewrite our linear program because the simplex method is going to proceed in steps, writing the whole linear program in this format is going to be a bit cumbersome. We are going to choose a different format. This format is often called dictionaries in the literature. Okay, so I'm just going to call them dictionary format. So here is the idea. Rewrite as a dictionary, and we will look at the formal definition of dictionary later. Okay, I prefer to go through examples first before getting into formalisms. So I'm going to start with the objective function, which is 5x1 plus x2 plus 4x3 plus 4x4. And then I'm going to write all of these variables, 5, 6, and 7, in terms of the other 4 variables, x5, x6, and x7. The first one is 17 minus 4x1 minus x2 minus 3x3 minus 3x4. So let me write the constant here. Okay, does everybody see how I wrote this? This is basically the first constraint rewritten in this manner. Now I want to look at the second constraint. It's going to be x6 equal to 4 minus whatever is on the left hand side. It's x1, x3, and x4. And now I'm looking at the last one, and it's going to be 10 minus whatever is on the left side. So it's 2, 1, 2, and 3. Those are the coefficients. Two, 1, 2, 3. Okay. Okay, let's make it slightly smaller so that we can see everything together. Okay. Are there any questions about how we wrote this? Z from now on will denote the objective function. Okay. So what we have here, the important points to note are that we have the objective function Z and variables x5, x6, and x7. All of these are written in terms of the other 4 variables, x1, x2, x3, and x4. Okay. And this is going to be our first dictionary. And for each dictionary, we are going to have a basis. The basis is going to be the variables you see on the left side, 5, 6, and 7. I will just write the indices, 5, 6, 7. Okay. And for each dictionary, we are going to have a current feasible solution, which you read off by looking at these numbers. It's setting x5, x6, and x7 to 17, 4, and 10, and all the other variables to 0. So it's 0, 0, 0, 0, 17, 4, and 10, what I wrote above earlier. Okay. Note that all of these are non-negative. That is important because all our variables are non-negative in the standard equality form. I'm not going to write that in the dictionary, nor am I going to say in the dictionary that this is a maximization problem, right? We are dealing with standard equality form. So I'm just going to write down as little information as I really need. The rest of the information is implicit. So the fact that these are non-negative is a crucial fact. All right. Any questions or concerns at this point? Is everybody fine with this way of writing the linear program? So that we can do the simplex method in steps without writing too many things and just keeping in mind what is important.
Sir, could you tell me why that non-negative part is so important for us?
Right. The fact that this is a feasible solution, why is it a feasible solution? It satisfies the equations, but there is something else we need to satisfy. What is that?
X should be non-negative.
Exactly. We want all our variables to be non-negative. That is part of the standard equality form, right? So that's why if you directly want to read off a solution, you want all of these numbers to be non-negative, right?
So what happens if we end up with a place, say we have -17 because of something that happened there?
That's not a valid dictionary. So we will come to that later. So if my
Okay.
LP was not the way I want it to be, then we need to do something else. And that we are going to discuss later. Okay. So I'm going to call this an easy LP. And the reason I'm calling it easy LP is because it has these two properties. One is there is an identity matrix here, and all of these are non-negative. Okay. Right. So we will talk about how to get to this form in future lectures, right? But today I just want to focus on this form. And if we start with this form, throughout the process, we will make sure that these properties are maintained. Okay, so we are going to go through a bunch of steps, and at each step we will make sure that we have these properties maintained. Okay. All right, so maybe let me make it a bit bigger again. Okay. Okay, good. Any other questions or concerns at this point? Okay, and what is the value of the current feasible solution? The value is the evaluation of the objective function. So we are evaluating this for the current solution, and that will just be 0, right? Because x5, x6, x7 will not even appear in the objective function. So the current value is 0. So now my question to you is, can we find a better feasible solution? Is there a systematic way to look at this dictionary and find a better solution? And the idea is we don't want to make too many changes. We want to formalize this procedure. So we are going to make incremental changes that will help us to eventually get to an optimal solution. Okay. So if you look at this dictionary, look at the objective function. The objective function is 5x1 plus x2 plus 4x3 plus 4x4. All the coefficients are non-negative. If I can increase any of these variables, x1, x2, x3, x4, which are all 0 right now, if I can increase any one of them, then I will be able to increase the value of z. Do you agree? Of course, if we increase some variable, we may also have to adjust other variables in order to get a feasible solution. Right? So observe the objective function. It's 5x1 plus x2 plus 4x3 plus 4x4. So the point to note is, if we increase any of x1 to x4, the value of z increases. So we are going to do that. And we are going to choose one of these four. I'm going to choose x1. Okay. Doesn't matter. You can choose any one. So let's choose x1. Okay. The question is, how much can you increase? Right now, x1 is equal to 0. So how much can we increase x1 by? And I'm not going to change the other x2, x3, and x4. I'm going to keep these unchanged. Okay. And this we are going to increase. This is our plan. While keeping x2, x3, and x4 all equal to 0. Okay. So can anyone tell me how much can we increase x1 by while keeping x2, x3, and x4 at 0? Let us look at these three conditions here. Can I increase x1 to 6?
No, x6 will become negative.
X6 becomes negative. Exactly. So we can't increase x1 all the way to 6. In particular, you note that you need to look at this part here, right? Because the rest are going to be 0. So we need to make sure that these quantities are all non-negative. 17 minus 4x1, 4 minus x1, and 10 minus 2x1. Okay, great. So how much can we increase x1 by? And we want all of these quantities to be greater than 0. Okay, I've just written down the red circled part here. We want all of these to be at least 0. This implies that x1 is at most 17 over 4. This implies that x1 is at most 4. And this implies that x1 is at most 5. Right? So, well, 17 over 4 is just 4 1/4. So the best we can do is we can increase to at most 4. And actually, let me write down x5, x6, x7 here. Okay. So it turns out that the best we can do is dictated by x6. Because this is in some sense, the strictest inequality among all of these, right? So we are going to increase x1 to 4 because that is the best we can do. And when we increase x1 to 4, x6 is going to come down to 0. Do you see that? So increase x1 to 4, and this implies that x6 will now become 0. And everything else will change automatically. We will talk about that. All right. So let's write down a new solution. Our new feasible solution is going to be as follows. Let's write down what we know, and the rest we will be able to read from the dictionary. Okay. So x1 is going to change to 4. Remember, we talked about keeping x2, x3, x4 unchanged. So we already know that the next three variables, x2, x3, x4 are 0. Once you know x1, x2, x3, x4, x5, x6, x7, you can just calculate looking at the dictionary, right? So x5 becomes 17 minus 4 times 4, and the rest is 0. So x5 becomes 1. x6 becomes 4 minus 4, 0, as we already discussed. And x7 becomes 10 minus 2 times 4, which is 8. So that's equal to 2. Okay. And what is the value of this new feasible solution? Let's go to our z. It is 5 times x1 plus x2 plus 4x3 plus 4x4. That just means it is 5 times 4, which is 20. And 20 is clearly greater than 0. Therefore, we have a better feasible solution. Okay. So now we have a new feasible solution, which is not 17,410. It is this new one. And its value is 20. So I want to ask the same question again. Can we find a better feasible solution? Okay. Can we look at this dictionary and somehow figure out whether it's easy to find another feasible solution that is better than the one we have currently? But do you see that there is a problem? We can't use the same technique again. So previously we were able to easily do it because we had a very specific format, and we were able to increase x1, and then we were able to figure out how much to increase it using this dictionary. But now it's not so clear what to increase and how much you can increase by. It seems more complicated than before. So what we are going to do is, we are going to write a second dictionary by doing some row manipulations, right? Basically, we are going to do some substitutions, and we are going to write a new dictionary in such a way that we can again easily find a better feasible solution, right? So the point is, it's not so easy unless we write a new dictionary. Okay. Okay, so what did we do before? In the previous dictionary, we referred to 5, 6, and 7 as our basis. So I want to figure out what is our new basis. That's easy to do. We increased x1. So x1 is going to enter our basis. And one of the variables, x6 in particular, became 0. So x1 is going to enter our basis, and x6 is going to leave our basis. Okay, so x1 enters and x6 leaves. Our new basis is going to be, instead of 5, 6, 7, it's going to be 1, 5, and 7. Notice that 1, 5, and 7 are these variables, and the other variables are actually 0. That is not a coincidence. That all happened by design, right? So we're going to write down a second dictionary. And the new basis is going to be 1, 5, 7. That means that we want to write the objective function and these three variables, x1, x5, and x7, in terms of the other 4 variables. x2, x3, x4, and x6. Right? So we want to write everything in terms of okay. So how do we do this? So far is the plan clear? Does everybody follow what we are trying to do and why we are trying to do it? Okay, so this is our goal. And how do we achieve this? We are going to look at this constraint here because 6 was the leaving variable. And we are going to write down x1 in terms of x2, x3, x4, and x6. And then we are going to substitute that in all of the other equations to get to our desired objective. Right? So notice that I can write x1 as 4 minus 0x2 minus x3 minus x4 minus x6. And if I substitute this in the other three equations, I will be able to write down everything in terms of 2, 3, 4, and 6. Okay. So this is the plan. So let's write down this equation. X1 is 4 minus x3 minus x4 minus x6. Okay. And now let's write down the others. I'm going to do 1 or 2. Let's see. So Z was 5 times x1 plus x2 plus 4x3 plus 4x4. Z is 5x1 plus x2, 4, and 4. Right? So instead of x1, I'm going to put down this right hand side. And the rest is going to be as it is. And this is going to be 20 minus 5, let's do x2 first. So 20 plus x2 minus 5x3 plus 4x3 is a minus x3. Minus 5x4 plus 4x4 is a minus x4. And minus 5x6. And that is what I'm going to write down in my first row here. 20 plus x2 minus x3 minus x4 minus 5x6. Okay. Is everybody following so far? And now let's look at x5. x5 was 17 minus blah, blah, blah. So I'm going to substitute x1 by the same right-hand side as we did before. And if you do that, you can check it yourself. I'm just going to copy down the dictionary that I created before the lecture. Okay, so far everything is correct. I think I haven't made any mistakes. And now it's going to be 1 minus x2 plus x3 plus x4 plus 4x6. Okay, let's just look at the coefficient. It was 17 minus 4x1, right? But x1 has been replaced by 4 minus whatever. So you get 17 minus 16, and that is equal to 1. Right? And then you can do the rest. Does everybody see how we are doing this? And the same thing with x7. It's going to be 2 minus x2 minus x4 plus 2x6. Observe that these three numbers are exactly what we had in these three positions, right? That is not a coincidence. The feasible solution is easily read by looking at the dictionary. So the current feasible solution is precisely 4 followed by 3 zeros, 1, 0, 2. Right? Which is exactly what we wrote earlier. And its value is basically what you see here. Okay, good. Are there any questions or concerns at this point? Does everybody see how we wrote down the second dictionary using the first dictionary by doing a single substitution, which was based on which variable is entering and which variable is leaving? In particular, we looked at the equation for the leaving variable and we wrote the entering variable in terms of the previous variables that were not basic and the new variable that has left the basis. And then we substituted this in all of the other equations to write down everything in terms of the new variables that are not in the basis. Right? So that would be 2, 3, 4, and 6 in this example. Are there any questions or concerns? If anything was not clear, this is a good time to ask. Let's resolve it. Okay. If there are no questions, you know what the next question is. Can we find, in fact, we already asked this question, and we noticed that it was not so easy to answer. So now let's go back to the same question. Can we now find a better feasible solution? And if so, how do you propose to find it? So I want you to look at this dictionary and tell me if there is any variable you can increase in order to get a better feasible solution.
X2, sir.
Sorry, which one?
X2, sir. It is
X2.
unique with A.
Exactly, X2. So let us look at the objective function. All the coefficients except the one for X2 are not even positive, right? X2 is the only one that has actually a positive coefficient. So if you increase the value of X2 while keeping X3, X4, X6 equal to 0, you would be able to get a better feasible solution. Of course, when you increase X2, you may have to adjust some other variables, but we won't change the X3, X4, and X6, right? So it's the same plan as before. Increase X2 while maintaining X3, X4, and X6 at 0. Okay. So how much can we increase X2 by? Can someone look at these three equations and tell me how much we can increase X2 by? This time it's easier to observe.
Just one, sir.
Just one, right? Exactly. Because we need X5 to be non-negative. So the best we can do is we can increase X2 to 1, and that will make X5 to be equal to 0, which is fine. Right? Okay. So can anyone tell me what is the entering variable and what is the leaving variable?
Leaving is 5, sir. Entering should be 2.
Exactly. Entering variable is X2, leaving variable is x5, and our new basis is going to be 1, 2, and 7. Okay. So we are going to write down, as you can imagine, we are going to write down a third dictionary, and the new basis will be 1, 2, 7. Right? And that means we want to write down all the z, x1, x2, and x7 in terms of 3 to 6. Okay. And how do we do that? Can anyone tell me what is the equation we should use to substitute stuff? Right. So this is our entering variable, and this is a leaving one. So we are going to look at the same equation in order to do our substitution. So in particular, we want x2 to be written in terms of 3, 4, 5, and 6, which is easy by just looking at this. So it's going to be 1 plus x3 plus x4 minus x5 plus 4x6. Right? And this we are going to substitute in all the other equations in this dictionary in order to write a new dictionary. Okay. In particular, this is already what we have written here. So can anyone do the calculation at their own end and tell me what is the first row? What is Z? Can you please do it?
21 minus x5 minus x6 now.
21 minus x5 minus x6. Okay. Can someone tell me the second row, x1?
So do we need to calculate that, sir? Like it seems like Z, like this should be a stopping point.
Fair point. Fair point. You are right. I'm just going to finish the dictionary and then discuss that matter, right? So I'll just write it down. But yeah, you're right. Already the x5 and x is about negative. So this is actually going to be an optimal solution. But anyways, I'll just put it down for completeness. So if you do the substitutions, you're actually going to get this dictionary. Okay, please check at your own end. Hopefully I haven't made any mistakes. Okay, so this is going to be our new dictionary. Let me write down the feasible solution, the current feasible solution. It's what you see here, right? So it's 4, 1, followed by a bunch of zeros and 1. Okay, and the current value is exactly what you calculate in the first row, which is 21 minus x5 minus x6, which is equal to 21. Observe that 21 is greater than the previous value, which was 20. So clearly this is a better feasible solution, right? And someone has already answered this. Can we find a better solution? We can't, because z is 21 minus x5 minus x6. So for any feasible solution, you are going to be subtracting something from 21. The best you can do is to not subtract anything, right? Subtracting some non-negative value. So right now we have 21 as the value, and that is the best you can do. There are no positive coefficients in this row. All of the coefficients are actually 0 or negative. So that is the key point. Since all coefficients are non-positive, we can't get right. In particular, this solution is an optimal solution to the linear program that we started with. I called it easy LP, right? So for that easy LP, we have found an optimal solution. Okay, good. So this is basically how the simplex method works. Now, different texts use different ways of explaining it. I personally find dictionaries to be one of the easiest ways to actually execute linear programming solving or execute simplex method on paper. Of course, typically people don't do it on paper. You have computer programs to do it. But I also find it one of the easier ways to understand what's going on. In the text we are using, GKT, can anybody hear a siren behind me? Yeah, so I think there is a fire alarm that has gone off in the building. Give me 1 second. Probably it is just, I think they are doing some sort of.
That is a mock alarm thing. We got one email from HOD, so you can ignore.
Right, it's a mock alarm, right?
Yes.
Oh, good, good. Okay, I didn't see that email. Thanks. Okay, thanks. So in GKT, the textbook we are I'm following, they actually don't use dictionaries. They use another thing called canonical forms, which is equivalent to dictionaries. It's a bit more difficult to follow. I might actually cover it, but I want to first cover dictionaries and then we might actually see it using canonical forms, just because there are some things that are clearer if you do it through canonical forms. So rather than just doing simple substitutions, in canonical forms, you actually have to compute the inverse of a matrix and stuff like that, which is not as easy to do on paper. But of course, if you're using the computations, it doesn't make a huge difference. Okay, so we might cover canonical forms later. So it's the same thing, but in a different way of proceeding. Right? So you'll be computing identity matrices by doing some matrix inversion stuff. Okay. So we still need to understand how to get a linear program in this form. So that's something we will be discussing in the next few lectures. First of all, your linear program may not even be feasible. So you may not even be able to get this form, because if you get this form, identity matrix and all values non-negative, it automatically means your linear program is feasible. So for an infeasible LP, you can't even get this nice format or the dictionary format. Okay, but we'll be talking about those things in the subsequent lectures. What we have done today is that if we have this nice format, then we can iteratively find better solutions, rewrite dictionaries for those solutions, and finally get an optimal solution. There is another possibility, which is that you get an unbounded LP. We will discuss that in the next lecture or in the next lecture. Okay, but I hope that the approach is overall method is clear. Okay. So that's all for today's lecture. We will